All right, and welcome to Unit 5 on circular motion and gravitation, lesson number 2 on horizontal circles. In this video, we're going to be discussing lesson number 1, but before we get to that, there's a couple things that I want to discuss. Now, the first thing is this notion of horizontal circles. I think many people probably get this already, but just in case, I need to mention it. So in this case, we are going to be discussing spinning objects around mainly on strings, but it could be on a track or a centrifuge, could be many things. The main idea behind these horizontal circles is that the axis of spinning is going to be the same as that of the ground. So we could imagine like our ground is here. Let's draw that a little bit differently. Let's say our ground is here, and our circle is going to be in line in the same axis as the ground. As opposed to, we could say a vertical circle, we're going to have our ground like this, but instead our circle is going to be more of like a vertical type thing. So this first example is what we're getting at here. We can imagine spinning a bucket around our heads. It's like orbiting our head, opposed to spinning a bucket by our side. All right, so with that said, let us get on to what a centripetal force is. Well, really, a centripetal force, any force, is just mass times acceleration. So we can say that a force is equal to mass times acceleration, except this centripetal force includes a centripetal acceleration. And a centripetal acceleration is just an acceleration moving towards the center of a circle. So as we spin an object around a center point, that acceleration is always going to be towards the center of the circle, right? If our object were down here, the acceleration would be towards the center. If it were here, it would be towards the center. All right. Now that said, this force centripetal value here, a centripetal force is just any force that acts to pull an object around in a circle. So if this thing leading out to our mass here were a cable, and we're spinning this on a cable around our heads, well, this centripetal force is really just force of tension, right? In a cable, we have tension force. Maybe we had like a large sun here, and this were a planet, and then this line wouldn't even exist. And this planet were orbiting the sun. Well, in that case, the centripetal force would be gravity. We could even say that this were like a loop-the-loop, right? We have a lead in, it's going to go around the loop-the-loop, and it's going to shoot off the other way. Well, in this case, which we haven't learned much of this yet, really it's going to be the normal force is what we would be looking at. The normal force would be pushing inside this track the whole way, causing the essentially vehicle to stick to the track and make it all the way around. Okay, so centripetal force, just really any force that keeps an object held in a circular motion. Cool. With that said, that out of the way, let's jump into this first example problem. I'm going to clear this, although in just a minute we're going to be writing it again. So this is a human centrifuge. A 76 kilo person is whirled in a horizontal circle of a diameter 9.00 meters. If the centripetal force on the person is 5.21 kilonewtons, determine the time for one revolution. All right, so a couple things that it has told us. Things that it's told us and also that we know. So we just erased this formula, but I'm going to say that centripetal force is equal to mass times acceleration, except that acceleration is circular or centripetal. Okay, now what do we have here? We have the mass given to us. The mass is 76 kilos. And we have the centripetal force on the person. That's kind of a new one. Well, it's new to you, but you'll see later we don't often get this combo. Well, right away, I think we can see we can solve for our centripetal acceleration. But we are still looking for the time for one revolution. So how are we going to get that? Well, if we solve for AC first, in the last lesson, we played with a little formula. We called it the period formula. And we said that, let's get a new color here. We said that AC is equal to 4 pi squared r over t squared. That's our period formula. So if we have AC, we can check that one off. We are looking for the radius of this. No, we're looking for the time of revolution. We are given the radius. My bad. Given the radius, and we are looking for time for a revolution or the period. Well, these are just, absolute values. So essentially, if we solve for AC, we can plug it into this formula and solve for period. That's our game plan. So let's see if we can pull that off. All right, back to magenta. So we can say AC is equal to centripetal force divided by mass, and we can put some values in there. What was that centripetal force? That was 5.21 times 10 to the 3 newtons. 1 times 10 to the 3 newtons divided by the mass, and the mass of this person was 76 kilograms. All right, and if we plug all that into our calculator, we get, I'm not going to round this one off too much, 68.55 meters per second squared. And we're going to take that and we are going to chug it into this. Except before we do so, I would like to rearrange this formula. So we're going to have t, well, I can even say t squared. You know what? Nah, I feel confident in your rearrangement skills now. So t is going to be equal to, I'm essentially doing a flip here, 4 pi squared r over AC, and this whole term is getting square rooted. So we plug some values in here, and we are going to get 4 pi squared times the radius, which was 9 meters, divided by AC, which was 68.55 meters per second squared. And it works out to a period of, I almost made a mistake here. So the diameter is 9 meters. Let me take this back. Glad I looked down at my sheet for a second. The diameter is 9 meters all the way across, but we just want the radius. So this is actually 4.5 meters. All right, and we plug that into our calculator, we should get a value of 1.61 seconds. It takes 1.61 seconds for this centrifuge to spin a person around. And that is all.